Okay, so this is going to be lecture 1 for Math160 on sets and functions. So we won't get too much into functions today. We'll save that for the double. But for now, I just want everyone to have the same foundation on where this mathematical stuff comes from. So firstly, what is a set? Okay, so a set, let's call it S, is a collection of unique objects. Okay, so we try to be as broad as possible because in mathematics we can have sets of lots of things. We can have sets of numbers, we can have sets of functions, we can have sets of quite a lot of things. So in general, it's a collection of unique objects. When we say unique, we mean that a set cannot have two of the same thing. So if you have a set of fruits, you can have apple, orange, pear. You can't have apple, orange, pear, and apple again. Okay, that doesn't work. So how do we denote a set? A set is given by S, and we can have S1 up to Sn. Okay, so this is an example of a finite set. We have n elements from S1 to Sn. Okay, so that's a little bit of jargon there. The objects inside a set, we call those elements. Now, each element in a set belongs to that set. If you give me some other element, there's a relation between that element and a given set. We say that some new object, let's say A, can be in the set. We use the little Greek epsilon symbol. So this is A is inside the set. That's one possibility. Or A is not inside the set. So we have the little epsilon symbol and we cross it out. So in mathematics, when there's always two cases that could happen, we have the one case like that, and then the other case we usually just cross out. Okay. For example, in this case, A is in the set or A is not in the set. You always have that binary going on there. Okay, so some examples of sets. We can have the natural numbers. Now there's a bit of debate on whether or not the natural numbers should start from 0 or start from 1. For this module, let's say that we're going to use the convention where it starts from 1. Okay, so whenever there's a question involving the natural numbers, unless otherwise stated, we're going to start from 1. Okay, so this will be 1, 2, 3, and so on. Okay, we all should know the natural numbers. Okay, one step up from the natural numbers is the integers. So those are the natural numbers plus 0, since we're not including that, plus all the negatives. So we have all the negatives here, negative 2, negative 1. Now we do include 0, okay, that's important in this case, 1, 2, and so on. Okay, it's very important that you understand these sets and what makes them up. Okay, one step up from that, we have the rational numbers denoted by Q. And as you can see in all these cases, we add that additional slash there. So it's not just a capital Q, it's a capital Q with the little slash like that. Okay, these are all the rational numbers. Now, the way I'm going to write this is with a set notation called restricted comprehension. I don't think you've seen that in high school, but we're going to use that quite a lot with regards to functions. The way restricted comprehension works is we write the element, let's say x is an element of real numbers. So we all know what real numbers are. Okay, all the numbers on the on the number line, sorry. So we say x is an element of the real numbers. This forms the bigger set. Now, restricted comprehension, we now restrict that set. So if we're going from all of the real numbers down to the rational numbers, we need to form some kind of restriction. How do we do that? We put some rule. So what rule does this x need to follow? x needs to be equal to a over b, where a and b are integers and b is not 0. Okay. Yes?
Sorry, what is the name of the set?
So this is the rational numbers. The process of writing that right inside there is called restricted comprehension. So whenever you have a larger set and you want to cut out some elements or show that you only want to deal with a smaller subset, we write it like that. Okay, so this is called restricted comprehension, and we will use it quite a lot when we look at the domain of a function. Okay, we'll get to that shortly. So this is restricted comprehension. Okay, so whenever I use that term, I'm referring to the fact over there, where we take a larger set, we add some rule to get a smaller set. Okay, and all the elements in the smaller set follow that rule that's on the extreme right there. Okay, and then as I said here, R, that is all the real numbers. Later on, we're going to be working with complex numbers. We'll get to that later. Don't worry too much about that. But for now, real numbers, you need to be comfortable with that. So I'm not going to put all the real numbers, but just some examples. Pi, that's a real number. Okay, everyone should be familiar with pi. Root 2, -1, -1 over 12, and so on. Right, any number that you could really think of, that will be included in the real numbers there. Okay, so please make sure you know the similarities and differences between these sets, because when we go on to functions, we're going to look at mappings between the sets. If we have a function going from the integers to the real numbers, that is very different to a function from the real numbers to the real numbers. Okay, it makes a very big difference with what set we are looking at. Okay, so those are some examples of sets. Now let's look at some set operations. Okay, so the first set operation is the union of two sets. So let's say we have a set A and a set B. We want to union them or join them together. We write that as A, like a U, but we don't finish any tails on the U, so it's just like that. A union B. So this is a new set. It contains all of the elements from A and all of the elements from B. And remember, when you're combining them, we're not allowed any duplicates. So let's just do a quick example to see how that works. So if A is 1, 2, 3, and B is 3, 4, 5, we want to form the union. So in other words, the set that contains everything from A and everything from B. So here, A union B, that's going to be 1, 2, 3. B already has a 3 there, and A already has a 3, so we only include it once, and then we have 4 and 5. Okay, quite simple, so everyone should be comfortable with that. Okay, number 2 is the intersection between sets. So that is A, and then it's similar to the U, just upside down, so it's like this. A intersect B. So if you think of like your Venn diagrams from grade 12, the intersection is your common place between the two sets. Okay, so it's whatever is in A and in B, okay? They share those elements. So we'll use the same sets as before, 1, 2, 3. B can be 3, 4, 5 again. Okay, A intersect B, what's that going to be? 3, good. Sorry, that's 3. Okay, just another little bit of jargon or definition. If we have a set that contains only one element, we call that a singleton set. Okay, so you might hear that come up in later lectures. If you hear singleton set, it means a set that only contains one element like that. Okay, number 3, set differences. So there is quite a lot of notation for set differences. Sometimes it's written A\B, A/B, and so on. We're not going to use any of that because that is too similar to some high-level math, so we don't want to confuse anything there. We're going to use this notation, A minus B. Okay, so that's one of the notations. If you just look on Wikipedia, you'll see that there. We're going to use this one and only this one. Please make sure you use that in test so I don't get confused thinking you are trying to do something else. Okay, so this is precisely what it says. We're going to take the set A and take away anything that's in B. Okay, like the usual difference. So A, let's use the same set, 1, 2, 3. B is 3, 4, 5. Okay, now we're going to take A and take away anything from B. So if I have A, I'll take away things from B. We see that A has a 3 and B has a 3, so we can take that away. That's fine. B has 4 and 5, but A doesn't have 4 and 5. Well, you can't remove something that's not there, so we don't worry too much about that. So 1, 2. Okay, so that is what we get for that. Okay, number 4. We're not going to use this so much, but it is important for your later years, and that is the Cartesian product. Okay, so you should all be familiar with the Cartesian plane, xy plane. So the way the Cartesian product works is we have A cross B. This is made up of, sorry, let's write it like this. So we can write it using restricted comprehension, like we did for the rational numbers. This is made up of ordered pairs A, B. So ordered pairs does exactly what the name says. Number 1, it's ordered. AB is different to BA. Okay, they're different like that. And pairs, well, there's 2 of them. Okay, ordered pairs. So we look at all the possible ordered pairs such that, so when you see that vertical line in restricted comprehension, you can read it as such that, and then the rule. So we look at all the ordered pairs AB such that A is from A. So we're using that symbol we saw before. A element of A or A in A means the same thing. And B comes from B. Okay, so that is the Cartesian product. So you'll be familiar with the Cartesian product R cross R. So R2, sometimes it's written as, that's your Cartesian plane. So whenever you did your graphing, you did it on the Cartesian product of the real numbers, x-axis, with the real numbers, y-axis. Okay, but we're going to look at other versions as well. So example again, so A, 1, 2, 3, B, 3, 4, 5. Okay, and we're going to look at the Cartesian product between the two. So A cross B, this is a set, all of the ordered pairs. So the way it works is you can imagine this as a table, okay, where A goes down the one side, B goes along the horizontal, and you just match them up. Okay, so let's take 1 from A, and then we can go 3, 4, 5 for all of B. So we take 1 and 3, 1 and 4, 1 and 5. Okay, that's like your first row, if you want to think of it like that. Okay, but this continues. We can take the 2 from A and 3, 4, 5. So we'll have 2, 3, 2, 4, 2, 5. Okay, so all of this, you can write it on one line, that's fine. Or you can write it like this table, that's fine as well. Means the same thing. Next, we can take the 3 from A and then do 3, 4, 5. Okay, so we have the 3 from A and then 3, 4, 5. Okay, and then we can close our set off there. Okay, so that is the Cartesian product between the two sets. Okay, any questions on the definition or the construction of it? Okay, and then the final thing, number 5, this is the power set. Okay, has anybody heard of the power set before? Okay, that's fine. So we have the power set, denoted by capital P for power, and then we give some set A. So we read this as the power set of the set A. If I provide you a set A, you can give me the power set of A. Okay, so how do we come up with this power set? So let's stick with the same A, 1, 2, 3. The power set is the set of all subsets. So we know what a set is. What's the subset? A subset is just a smaller collection of elements from the original set. So here we've got set A. If we construct a new set with just the element 1, that's a subset. It's a new set, and it contains elements from the old set. The set 1, 2, that's a subset. Why? Because 1 and 2 came from A, we made a new set from it, we call it a subset. The set 1, 2, 3, that is also a subset. Okay, I know what you're thinking, but yeah, it is a subset. Why? Because it's a new set constructed from the elements from A. However, the full set is not a proper subset. A proper subset is not including the entire set, and it's also not including the empty set. Okay, what's the empty set? It's the set that doesn't have anything in it. Okay, so we'll have a look at that now. So the power set of A is given by all the possible subsets, and we usually go in order of how many elements there are. So we start off with the set that doesn't have anything. We call that the empty set, given by this Greek letter phi. So this just means the set, sorry, you can write it like that. It's just the set with nothing inside. That's a perfectly valid set to have. Okay, so that is the set of 0 things. Now we go up and we look for the set containing 1 thing. We have 3 possibilities. The set containing only 1, singleton set containing only 2, and the set containing only 3. So 1, 2, and 3. Okay, now we look at the sets that contain 2 things. There's 3 possibilities, so we've got 3 things. There's 3 ways we can pick 2 things out of that. We can have 1 and 2, 2 and 3, 1 and 3. So let's put that here. 1 and 2, 1 and 3, 2 and 3. Sorry, that's a 3. Okay, so there's 3 of those. And finally, the set containing 3 things, well, that's the entire set. So you can write out the entire set, or you can just put A. It means the same thing. Okay, so this is the power set. Okay, and there's 1 or 2 questions in the tutorial looking at the power set. Okay, so tutorial 1 should be up. Please have a look at that. Okay, I remind you that the tutorial 1 will be due next week, Tuesday. Okay, so that is the power set. Any questions on that? Okay, I remind you again, if you are lost, please speak up now, because if you are lost later on, you will not catch up. Okay, yes, you lost. Yeah, that's fine. Okay, if you say you lost, I can go back. Where did I lose you? All of it. For the power set, or right from the beginning? From the power set. Okay, so the power set. Okay, I have no problem going over work again so that you understand. Okay, so the power set is a new set that contains all possible subsets. Okay, so what's a subset? So given a set, we construct a new set containing some or all of the elements from the original set. So if we look here at A being 1, 2, 3, we want to look at all of the sets we can make with those elements. So the first thing we can do is pick none of the elements. That's the possibility. In that case, we get the empty set, because it's literally empty. It contains no elements. Okay, so that's the first possibility. We could choose one element. Now, how many one element subsets are there? Well, there's 3 elements, so we can pick the first one and make a set out of it. We can pick the second one and make a set out of it. And we can pick the third one and make a set out of it. Those are the 3 singleton sets that we have there. Next possibility, we pick 2 elements. So how do we pick 2 elements? Well, we can pick 1 and 2, that's a subset. We can pick 1 and 3, that's another subset. We can pick 2 and 3, that's another subset. And that's all of them, right? If we picked 3, 2, well, that's already there. Or if we picked 3, 1, well, that's already there. 1, 3, 3, 1, same thing. Okay, or if we pick 2 and 1, that's already there. We've already got it. Okay, so those are all the 2 element subsets. What about the 3 element subsets? Well, there are only 3 elements. So we just pick all of them. So we have that set at the bottom there, 1, 2, 3. Well, because we picked 1, we picked 2, we picked 3. There's nothing else to pick, so that's it. What about 4 element subsets? Well, the set only has 3 things. You can't pick 4 things from 3 things, so we stop. Okay, and that is all the possible subsets. Better? Okay, cool. Okay, so it's all possible subsets. So in this case, we picked no elements, 1 element, 2 elements, 3 elements. Okay, we could look for 4, but we know that the original set only has 3. You can't pick 4 from 3, so we stop there. That's everything in the power set. Okay, a little bit of homework. Okay, so like I said on that Learn 2024 page, okay, so I went through all the assessments, tutorials, that's the weekly homework. I will also give you daily homework like this. This is non-compulsory, okay, so I'm not going to check your work for this. Solutions won't be available. You can come to my office if you would like to go through the solutions. But this is very good to go through because a lot of the test questions come from the homework questions. Right? Okay, so homework. A is given by A, B, C, D. Find the power set of A. Okay, so slightly more difficult because we don't go up to 3 element sets. Here we go up to 4 element sets. Okay, slightly more difficult. I won't give you anything more than that because at that point it just becomes a counting problem. Okay, but as long as you understand the fundamentals of it, that's fine. Okay, so if you can do it for a 3 element set and a 4 element set, I trust you know what's going on. All right. Any questions before we move on? Okay, so to summarize sets, we know what a set is. It's a collection of objects. Okay, given another object, it can be either in the set or not in the set. We can construct a set from another set using restricted comprehension. In that case, we're looking at a particular subset where those elements follow a rule. Sometimes the rule's given, sometimes you have to come up with the rule. In either case, it's some rule that narrows down what we're looking at. Okay, then there's set operations, union intersection, Cartesian product, power set. Okay, little example on the power set. Okay, so everyone's okay with sets. Okay, and please make sure you are familiar with those sets we looked at the beginning. Natural numbers, integers, real numbers, rational, irrational. Okay, I didn't put irrational as an example, but everyone knows irrational numbers are real numbers that aren't rational. Irrational, not rational. Okay. So now we're going to look at functions. I would like you to forget whatever you know about high school functions. Please delete that from your memory, but keep the trig functions. You'll need to know that. Delete everything else. So, what is a function? A function is a mapping between sets. Whether you are looking at first year university all the way up to PhD level mathematics, a function is always a mapping between sets. So what do we mean by that? Let's say we've got a set X and a set Y. X contains some elements. Let's call them X1, X2, and X3. Could be a finite set, could be an infinite set, doesn't matter. It's a set, we know what a set is. Set Y, sorry, that's a Y, not a V. Y1, Y2, Y3, Y4. Y is another set. Unrelated to X, right? Just another set. Could be a finite set, could be an infinite set, whatever set. So what do we mean by a mapping between sets? Okay, we know what a map is. It allows us to go from here to there. Exactly the same idea. We start with X, we want to go to Y. The function or the map tells us how we get there. So from X1, we can go to Y1. X2 can go to Y3. X3 can also go to Y3. Why not? That's a function. Looks nothing like what you did in high school, but this is a perfectly valid function. Let's make it look more like what you did in high school. Let's give this function a name. Let's call it f. F for function. Okay. Now, I don't want to draw these circles every time I want to share this function with someone. So I'm going to write out what the mapping does a little bit differently. So instead of drawing a picture, we're going to draw it like a mathematician would. We first provide the function name. That's going to be f. Dot, dot, colon. Okay, that's the end of the function name. Then we provide where we are going from. That's the set X. We draw an arrow, right? We're going from X to Y. Just like how we have a map going from Howard College to Westville campus, right? So from X to Y. Now we need to say, how do we get from X to Y? The way we do that is by the function definition. In other words, we simply write out f of x1. We take x1, what happens to x1? It goes to y1. F of x1 equals y1. That's what we mean by the mapping. F takes x1, or it eats up x1, and gives you y1. Okay, what about x2? x2 goes to y3, so we write f eats up x2, it goes to y3. We're just writing it differently. It's exactly the same as the picture, maybe a bit nicer like this. Okay, what about x3? Well, x3 also goes to y3. No problem with that. All we said is the mapping from x to y. You can have all the elements going to one element. You can have all the elements going to none of the elements. Doesn't matter, as long as you provide the rule. So f of x3, that's also y3. Now there's an important thing, very, very important thing. The set x. You see how all the arrows come from the x elements. We didn't leave out any x elements. For a function to be a function, we need to use all of the elements from that beginning set. We cannot leave anything out. That beginning set we call the domain. That set y, in high school you called it the range. That is not the range. That set Y is called the target. Okay, so like I said, please delete what you know from high school. Your teachers lied to you. It's called the target. So F, function name. X, domain. Y, target. Now, in high school, you came across the word range. What is the range? The range is the elements that we actually use from Y. It may not be all of Y. It may be some of Y. It may not be anything in Y. Whatever it is, we call that the range. In this case, we know that the target is Y1, Y2, Y3, Y4. Those are the elements in Y. What's the range going to be? Okay, first element in the range will be Y1. Next element, not Y2. There's no arrow going to Y2, not in the range. Y3. What about Y4? No. Does it matter that Y3 comes from two elements? No. Why? Because we're not interested in X. We're looking at the elements in Y that are being used. That's Y1 and Y3, nothing else. That is the range. Okay, so let's write that down. X is the domain. Y is the target. Now, there are a number of ways of writing down the range. I will accept any of them as long as it makes some sense. So we can write the range of F, if you want to write it out fully like that. So fully range F. Sometimes RF, capital R for range. The way that I'm going to use, and probably in the solutions and memos and so on, I'm going to write it as F, capital X. If I write F with a little x, that means the mapping from the set X to the set Y. F of the entire set is I'm mapping all of the elements, but that's just the range. So F of everything inside Y, that is the range. So F of everything is a set of all the elements in Y such that there's some X that is equal to that Y. Okay, we're using restricted comprehension. Why restricted comprehension? Well, because not all of the target might be used. Maybe some of the target is used. Whenever you think to yourself, some of the set is used, restricted comprehension. We had the full set Y, but we're not using the full set. We're using only the elements Y that came from some X, F of X. Okay. And then this is going to be a subset of Y, and the way we write subsets is like this. Okay, you might have seen that before. Okay, so that little curly thing, that's a subset, and then we put the little line underneath. So what this technically means is subset or equal to, much like you write less than or equal to. That's just any subset. If you leave out the line at the bottom, it's a proper subset, much like how you have less than, which is not less than or equal to. Does that make sense? Okay. So we see that the range is a subset of the target. This is the fundamentals of functions. If you do not understand this bit, when we move on, you're going to have some fundamental mismatch going on, right? Please make sure that you understand this before we get into the technical stuff. Okay, so here we drew a nice picture. We had a set X, we had a set Y. We wrote it like this. It's a bit better writing it like this, but what happens if your set X has 1,000,000 elements or infinitely many elements? You can't list it out. So listing it out like this is an explicit definition. You are explicitly writing everything out. We could do it implicitly. In other words, you don't list everything out, you provide some sort of rule to do it. So here, you can't really write out a rule, you're stuck writing everything out. However, if you have some rule, it makes it a lot easier. And this is what you were doing in high school. So we have f from x to y. Now, instead of writing every single f of every single element in x, we instead provide a rule. We take some element, little x, from capital X, and we map it over using a rule. And it's done like this. Okay. So I will put the rule in now, but for now I'm just going to write f of x. So we use this little arrow with the line on it. It means x gets mapped to f of x, and then here we can provide some sort of rule. F of x like that is an element in the set, and we can provide some rule on how we get there. For example, f from real numbers to real numbers, okay? So maybe you didn't even write this in high school. Maybe you just wrote the rule and you didn't really pay much attention of where you're going from and where you're going to. Okay, so this is going to be wrong for now, okay, but it just illustrates the point. So here we have an element x getting mapped to root x. That's the rule. You give me an x, I give you root x. It's a rule. It's how we go from the real numbers to the real numbers. Now, remember what I said about the domain. Everything in the domain needs to be used. What's the problem with this as our domain? There's a very, very big problem. Yes? Can't have negative. Good. Okay, just another thing I didn't mention. If you answer questions, you get points. At the end of the semester, points get converted into marks. So for your class test, I can add up your points, add it to the class test. You could end up with 150%. And I'll put down 150%. Okay, all the way up to the end of the year. So you get some points for that. Okay, good. We can't have negative numbers. So we can't have the entire set R. That contains negative numbers. So this doesn't work. Big problem. So we're going to redefine it so that it does work. Is there anything wrong with the target? If I take the root of a real number, let's say it's positive, so it works, what is the output going to be? Positive real number. Right. But it's still a real number, so it's fine. If I put that as integers, would we have a problem? We would have a problem. Yeah, the negative. And if we put in 2, we get root 2. Root 2 isn't an integer, so it doesn't work. See, this is why I say it's very important to know your sets of numbers, what and what doesn't work with these functions. Okay, so let's say we're going to redefine this with some x and some y. We're going to have the same mapping x to root x. Okay, as he said, we need to think about this x. Real numbers are fine, but they can't be negative. So think for a bit. Real numbers are fine, but they can't be negative. We're looking at a smaller subset of real numbers. What do we do when we're trying to consider a smaller subset? Restricted comprehension. Good. Extra points. Okay. X is equal to, well, we said real numbers are fine, but they can't be negative. So we can write it like this. X is greater than or equal to 0. That means non-negative. It can be 0. 0 is fine, but it cannot be less than 0. So greater than or equal to 0 is the opposite of less than 0. Okay, or the negation of it. Okay, opposite, negation, whatever suits you. Okay, so that's the set x. What about y? Well, the output is going to be a real number. It's going to be a positive real number, but that's fine. We can have more elements in the target than we need. So let's just say it's all of the real numbers. That's fine. Okay. So this seemed like a pretty long process, but in high school, when you got given a function, and the question said, what is the domain of the function? This is what you're actually doing. You've got a function, typically from the real numbers to the real numbers, and you need to think to yourself, where does the function break? It breaks somewhere. In this case, breaks for negative numbers. We need to remove that from the real numbers, and we're left with the domain. Okay. Let's look at another example. Okay, so I'm just going to leave it as x and y. We can fill in the gaps there. X gets mapped to 1 over x plus 1. That's the rule. You give me an x, I can compute that, and I can give you back f of x. So this, over here, this number is f of x. Okay. Now, I've given you the rule, and the rule can break sometimes. Whenever the rule breaks, that can't be part of the domain. The domain is all of the elements that we use. Well, we can't use elements if it's going to break the rule. They need to be kicked out. Now, 1 over x plus 1, those are real numbers. Everything's fine. Let's start with the real numbers. Most of the time, we're going to start with the real numbers. So, x is equal to, let's start with the real numbers. Right, that's the biggest set we know of right now. So, start off big and we can cut down to size. Such that, well, now we need to put in the rule. We can either have the rule saying only these values, or we can have a rule saying not these values. Same thing. We're accomplishing the same thing. So in this case, what can we not include? 0. So in the restricted comprehension, x cannot be 0. Or let's just write that. X cannot be equal to 0. Remember what I said at the beginning? X can be in a set or not in a set, and we put the cross through. X can be equal to 0, or x cannot be equal to 0. Here we just put the line through, and we're saying it's not equal to 0. That's fine. Everything's sorted. Is there any other point where the rule breaks? Yes, you can write that as well. You could write it as x being less than 0 and x being greater than 0. That's fine as well. It means exactly the same thing. Okay, remember with maths, I don't know if your high school teachers told you this, there's more than one way to answer a question. Okay, maybe your high school teachers didn't like that so much, but for me, if it's mathematically correct and I can see what you're doing, you get the marks. You can say x is not equal to 0. You can say x is less than 0 or x is greater than 0. That's fine. It means the same thing. I know what you mean. I'll give you the marks. Please work with what's comfortable with you, provided it's mathematically correct. Okay, another one. Okay, I hope I haven't lost anyone yet. Everyone's okay with this idea of domain. Okay, we start off with this big set. The real numbers is the biggest set we know for now. We start with that and we cut out the elements we don't want, or we explicitly say the elements we do want. And that's the domain. Okay, looks a bit more complicated, but same idea. We start off with the big set. We look for where there's problems. We don't want problems, we want to remove them. So here, we've got the root. Like we had before, the root should start ringing alarm bells. You cannot take the root of a negative number and get back a real number. Okay, later on when we do complex numbers, we'll change that, but for now, we have that. That thing there is the root of something. Okay, don't look at all of it together all at once, too much. Look at the outside, it's a root. Again, alarm bells. Root of something, doesn't matter what it is. It may look complicated, forget it. It's something. That something cannot be negative. So what do? We look for where that something is negative and say, no, we don't want that. Okay, so let's have a look. Okay, again, alarm bells. So this something here cannot be negative. Let's see where it's negative and say, no, we don't want that. We're going to remove it. So, x squared minus 1 less than 0. Again, a lot of warnings. This is what we do not want. We do not want that something to be less than 0. So once we've done all our calculations, we need to say whatever the solution was, kick it out. Okay, well, let's find them. Let's factor this quickly. So x plus 1, x minus 1, less than 0. Please, if you cannot factor quickly, go and look at that matric workbook that I've got there. I think it's the very first page. I go through 3 different ways of factoring something. Please find something that works and do as many examples as you can. Because if you make a mistake with this factoring, your next line is wrong, and then the next line is wrong. Your final answer is wrong. What part marks can I give you? Okay. Okay, so we've got this. We've got our possible values where this is 0, 1, and minus 1. So let's draw a number line. Okay, I don't know if you know this method, but just bear with me for a bit. So we have minus 1 and 1. Those are the intercepts of this. It's where it's 0. That parabola over there, ignore the less than 0. Don't worry about that. That's a happy face parabola because it's 1x squared. It's a happy face. So it looks like this. Okay, roughly, happy face parabola passes through minus 1 and 1. How do we know it passes through minus 1 and 1? Well, we factored it, so those must be the roots. It's happy face. Now we go back to the line and say, where is it less than 0? Well, less than 0 means below the x-axis. Well, there's the x-axis. Where is it below the x-axis? Between minus 1 and 1. So if x is between minus 1 and 1, that inside part there is negative. We do not want that. So let's write here problem with x being between minus 1 and 1. If x is equal to 1, we get 0. 0 is fine. Roots of 0 is 0. No problem. If x is minus 1, we also get 0. That's not a problem. We can take the roots of 0. That's fine. Anything between that is a problem. We want that out. So, what is okay? Well, everything outside of that region. So, what does that mean? It means x is an element of, we can write it like this. I'm going to write it a number of ways. You can see what works for you. So, minus infinity up to minus 1. Square bracket means we include that point. Round bracket means we don't include it. And of course, we can't include minus infinity, so default round bracket. And this new thing that we learned here, union. Why union? Well, we can be on the left-hand side or the right-hand side. Those are safe points. Union, everything on the right. Well, we're going to start from 1 up to infinity, round bracket, because we can't include infinity, default round bracket. Okay, so x is an element of that set. Well, that set is our domain. We can write it like that, or we can write it like this. X is equal to minus infinity to minus 1, union 1 to infinity. That's our set. That's our domain. It's all the points where we don't have problems. Between those square brackets is going to be that interval. That interval gives us a negative value for that function in the root. We don't want that. We have excluded it. So that's the domain. What about the range? Or should I say, what about the target first? What is the target for this? Remember, that's up to us. This is our function. We're defining it. Real numbers, perfectly fine. Could we put integers? No, we can't put integers. Why? Because if I put, let's say, 2 inside there, 2's from the domain, which means it should be in the target. If I put 2, I get 2 squared, that's 4. 4 minus 1, that's 3. Root 3. Is root 3 an integer? No. Well, the rule didn't work. So clearly, the target that we chose doesn't work. So it can't be integers. Let's be safe and put real numbers. Okay, so we've got this x. We can say f goes from this x, I'm not going to rewrite the whole thing, to the real numbers. That's perfectly fine. X gets mapped to root x squared minus 1. Okay. Okay, so that is looking at the domain, and we did a little bit of looking at the target. Now, for this next example, we're going to look at the domain, the target, and the range. We need to provide all of that. Okay, so this example here, from x to y, we don't know what these are. That's up to us to define. X gets mapped to the sine of root x. Okay, so here we've got a little mess of functions there. We've got sine on the outside and the square root on the inside. Don't worry about that. That's just the rule. We don't actually need to calculate anything with that. All we're looking for are where the problems are. Later on, when we look at composition of functions, then we're going to worry about this composition, as we call it, of functions. That will come later. For now, that is just a rule. We're going to see where does the rule break. Okay, let's start off with the domain. What's a good starting point? Okay, we're going to use restricted comprehension. What should the biggest set be for us to start? We had it for all of these problems. We had the same thing. Real numbers. Good. We could start off with the integers and then say we only consider positive integers. That's fine. You can do that. But for our purposes, we're going to be working with real numbers, so we start with real numbers. Remember, function definitions like this are up to us. We define the function. If we want to work with integers, we define the function to only work with integers. But we want to do calculus, and that needs real numbers, so we use real numbers. That's what was left out from high school. In high school, your teacher said, no, real numbers, here's the function. No, we have more control than that. Okay, so we start off with real numbers. Next, we look for places where things could go wrong. Dividing by 0, taking the roots of a negative number, and so on. Okay, where could things go wrong? Okay, for most of the questions, those are the only two, really. Later on, when we look at logarithms, you should have done that in high school a little bit. There's also problems with that function. We'll get to that. For now, division by 0, alarm bells. Roots of a negative number, alarm bells. Here, sine, not so many problems with that, right? Sine of something, we know how to deal with that. But inside, there's a root. Root gives you alarm bells. Okay. Root x, which means the sine of something, that's fine. But inside that something, that root x, that x can be positive. More specifically, non-negative. Okay, but yeah. So, the domain. X can be any real number. Y, any real number. Well, that's for us to decide, but we want to do calculus, so we pick real numbers. It's the biggest, nicest set that we can work with. Such that, or but, some rule, something to restrict what we have. That x inside there cannot be negative. So, x is greater than or equal to 0. Or we could write this as 0 to infinity. Same thing. We can write the set using restricted comprehension. That's fine if you want to put in the rule. But that rule means exactly the same thing as what we have there. Both are fine. You put that down, you get the marks. I'm happy. Okay, what about the target? The sine of something. Let's call it a real number. will that be always an integer? No. Will it always be a rational number? No. Sometimes it's rational. Most of the times not. What about a real number? Yes. So that's good. We can put that down. No problem with that. We can put that down as the target. Now, for those previous examples, we were ignoring the range. Okay, we'll go back to them. But for now, we're going to look at the range of this function, the sine function. What is the range of the sine function? Ignore the inside. Okay, ignore the inside for now. Okay, so we know that that inside part's not going to be negative. That's fine. We know sine going positive and negative looks the same, right? Okay, so whatever sine does for the positive values, the negative values are very similar. It doesn't go crazy for negative values, right? Okay, so the sine function for positive real numbers. What is the lowest point for that sine function? If there is a lowest point. Not 0. -1. -1. Remember, it oscillates up and down. It doesn't go below -1. What about above? 1. We say that it's bounded between -1 and 1. So, can it be 2? Okay, can't be 2. Will 2 be in the range? No, it can't be 2. It won't be in the range. Can it be a half? Yes, can be a half. That's in the range. So we've got two things now. What about 0? Can it be 0? Yes, it's in the range. Can it be minus a half? Yes, so it can be in the range. That's fine. Can it be anything between -1 and 1? Yes, nothing's left out. Going from -1 to 1, it goes through all those points. Doesn't go past those points. So, what's the range? -1 to 1 with nothing left out. Okay, so I'm being very, very particular with these examples. Okay, it might seem a bit obvious, but you need to be very, very rigorous with your thinking. Think about, is it in the range? Is it not in the range? Why is it in the range? Or why is it not in the range? You need to be thinking about these things. When we get onto the more advanced topics, maybe one point completely messes up the theorem. Not even applicable, because x is 0. And if you just go and use the theorem because you think x can be any real number, you get the whole thing wrong. Okay, so it's very, very important to be critical about these things. Okay, let's have a look at another example. So f goes from x to y. We'll look back at that previous example that we had, where it was 1 over x plus 1. Now, we already did the domain. X can't be 0, everything else is fine. Yes? So the target here is everything that we're mapping to. So this function here maps to real numbers. So the target is real numbers. But that's not necessarily the range. The range is the particular values that it gets mapped into. Like that picture we had right at the beginning, the target was y1, y2, y3, y4, but the range was that specific values that we went to. Okay, does it make sense? Okay. Okay, like the sine function, the output is a real number. So the target is the real numbers. But the range, it doesn't go above 1, it doesn't go below -1. So the range is that little bit there. Okay, even though the target is real numbers. Okay, so back to this one. We see that 0 is not in the domain, so we're not even considering 0. 0 out of our mind. We've dealt with that. What is the range? We know that the target is all of the real numbers. Okay, so we have that to start with. But the range is the numbers that we actually get to with the mapping. So let's pick an x value and see where does it actually end up. let's say x is minus 1. That's fine. Minus 1 is perfectly valid. It's not 0. We put in minus 1, we get minus 1 plus 1, 0. So we get 0 at the end, which means 0 is in the range. Because it came from the rule, so by definition, it must be in the range. So that's one value. What about if x is 2? Well, then we get 1 plus a half, so that's also in the range. And we can pick other values and we can see what's in the range. Now with this one, there's quite a lot of values that are in the range. There's one value that is not in the range, and it's easier to find what that is. Which value out of that rule can we not get to? That's easier to look at. Positive 1, exactly. Why positive 1? Well, that's a hyperbola. We know what it looks like in our head. It's something like this. Okay, so that's just a general hyperbola, right? Looks like that. But it's shifted up by 1. Shifted up by 1 means that's our new asymptote. Asymptote means we never get there. Well, never get there, well, that can't be part of the range, because we never get there. Okay, so that's not in the range. So the range is everything. Look at the vertical. We reach everything along the vertical except 1. So that's not in the range. So here, the domain, let's write it using intervals. Why not? So that is going to be from minus infinity to 0. We don't want to include 0, but everything else is fine. This is a perfectly valid set, and so that makes up the domain. Notice how we use round brackets on the 0. Round brackets mean we do not include that point. You could have written this using restricted comprehension like we had before. Both ways perfectly fine. Please pick whatever suits you best. But with tests, don't mix and match things. Okay, if you like this way, stick with this way, it will be easier for you. Okay, don't answer one question one way and then another question another way. Too much to focus on. Why? That was the range. Range is the outputs, right? Target, yeah. So if we put some value there that we can put in, we get a real number. Well, that's fine. We can put the target as real numbers. No problem there. What about the range? Yes. In our cases, yes. Yeah. So when it comes to other functions, or in the tutorials, maybe I'll put a funny target, but for when we do calculus, real numbers. Okay. So this is all just background stuff, and then once we get into the calculus, it's real numbers to real numbers. That's how we do calculus. Okay. But maybe there's one tutorial question where it's a bit funny. Okay. And then the range, that's everything except 1. Let's write it as an interval. Minus infinity to 1. Round bracket, we're not including 1. That covers the negative case up to 1. Everything after 1, that's fine as well. So we take the union from 1 to infinity. Okay. So here I wrote it as a union of intervals. Okay. Just a note on that. That first bit, that's an interval. That second bit, that's an interval. The union of the two, that's not an interval. An interval has a start point. We include everything up to the end point. Here, if we look at the whole thing together, we're not including 1. So altogether, it's not an interval. Please do not write that whole thing is an interval. It's made up of 2 intervals, but together it might not be an interval. Okay. Okay, we want to be mathematically correct with these things. Okay, everyone happy with that? Okay, so let's write something really crazy down and work our way through it. F goes from x to y. X goes to. Okay, at the top, let's put sine of x. Okay, now we're going to build up a denominator. Let's say cos of x, right? Let's I feel like trig functions, plus a half. Okay. It's fine. We know how to work with trig functions, no problem with that. So the top is fine, the bottom is fine, but we've got a division there. And that, again, alarm bells. What can we not divide by? 0. So when that bottom part is 0, problems. We want to remove those cases. Okay, so let's start off with the domain. And we're going to use restricted comprehension. Again, there's multiple ways. I'm going to use this way for now. So, restricted comprehension. The sine function we can put inside real numbers. That's fine. The cos function we can put inside real numbers. That's fine. So let's start off with real numbers. Such that. Now we need to put in a rule. The sine function. Are there any restrictions on that input? No, we can put whatever we like in, we're going to get something out. The cos function, are there any restrictions on that? No, just the cos function. Not the denominator, just the cos function. Anything? No, cos function, we can put whatever we like. But what about the denominator now? If that denominator is 0, we have problems. So, let's put that down as a restriction. It can't be 0. Okay, that's perfectly fine. You can write it like that. But you're not going to get all of the marks because we can do a bit better. That cos x plus a half not equal to 0, it doesn't tell us exactly the x values. It's perfectly fine as a rule, but we want to know which x values should we include and should we not include. So let's do a little bit more work. Maybe we can get some bonus marks in the test if we do that. So, we want to find where all of them are not 0. Well, that's a bit difficult. Let's find where they are 0 and kick them out. So, we put a whole lot of exclamation marks because this is an intermediate step. We're looking for where it is 0, but you need to keep in mind that's not the answer. We're looking for where it's not 0. So, cos x plus a half equals 0. Again, warning, this is not the answer. This is just going to help us get to the answer. Okay, cos of x plus a half. That's quite easy. Let's just take the half over quickly. So we have cos of x is minus 1/2. Okay. We're going to get two sets of solutions. We're going to get the solution closer to 0, like that acute angle kind of thing, and then the other one. Okay, you should be familiar with what I'm saying, right? The two sets of solutions. Okay, if you don't get what I'm saying, let's draw a graph. Something like that, that's a cos graph. We're looking for where it is equal to minus a half. Maybe that's somewhere here. We get one solution here. Okay, so it's not acute, but it's the one closer to 90, if you want to think about it like that. And then we have one on that other side as well, we've got over here. Okay, there's always going to be two. Same thing with the sine function. You've got a sine function, you try cut it somewhere, you're going to have one solution on the one little bit where you go up the hill, and one where you go down the hill. Okay, same thing here. Now that first solution, quickly check on your calculator, what is it going to be? A little bit after 90. It's a special angle, so you should know it immediately, but 60. No, it won't be 60. 60 is where it's going to be positive. Okay. 120, that's going to be that second one there. There's another one. Okay, think about it. You got the graph, okay? So you've got 1, cos of 60 is a half, okay? So where does it go to minus a half? Okay, maybe this is a good point to show you this here. Okay, if you're ever stuck with graphs, please go to this website called desmos.com. It's very nice, very simple to use. You go here, you type in what you want, so let's say cos x, and it sketches the graph. What's nice about it is it shows you all the intercepts. Okay, don't worry about that. Let's put this on degrees. Okay, we will cover this a little bit later. There are two angle measures that we're going to be using. For this lecture and only this lecture, we're going to be using degrees. That's what you know from high school. 360 degrees makes up a full circle. After this lecture, we are going to switch to another angle measure called radians. Any of you heard that before? You have heard that. Okay, so instead of going 360 around for radians, we go 2 pi around. Right? 2 pi r, that gives you the full circumference. We'll discuss that later. Let's use degrees for this example. Okay, so we've got cos x. We want to see where is it minus 1/2. So we can say y equals minus 1/2. And then that gives you this blue line. And you can see it cuts the 2 points like I showed in the notes there. You just tap on the point there, and it gives you the 2 things there. Okay, so 120. I think someone said 120. Okay, and then the other one there, 240. Okay, so we've got the one and we've got the other. Did anyone say 240? I think I only heard 120. Okay, anyway, 120, 240, but that's just on this little bit of the cos graph. We know that it goes forever that way, forever the other way, in integer steps of the wavelength of it. You've heard wavelength, right, of the thing. Okay, so the full cos graph is 360. So whatever our solution is, we're going to get another solution by adding 360. We add another 360, we get yet another solution. Minusing 360, we get another solution. Minusing another 360, we get yet another solution. It's always in those integer steps. So x is equal to 120, as the one person said, plus k 360, where k is any integer. We can go 1 step, 2 steps, 3 steps, as many graphs as we want. That's one, and then we get x is equal to 240, that's the other one. We can use k as well, that's fine, k 360. Okay, so this gives us infinitely many problem points, right? That's a lot of problem points, but we know how to deal with it. If this is a problem point, we just remove it. So, how do we remove things? Restricted comprehension. So we're going to rewrite this. X is equal to, can be any real number, that's fine. X cannot be the problem point. Remember, that top bit and that middle bit there, those are the problem points. We do not want the problem points. X cannot be equal to the problem point. Okay, and then just underneath here, I'm going to put the other one. X is not equal to 240 plus k. Maybe you can put another integer. Let's call it L. Okay, right, they're independent solutions. So we can put 2 integers for that. And then maybe on the side here, to remind us, k, L are integers. Okay, so that handles that division by 0 case. Are there any other problem points? Anything else we need to worry about? No, it was just that division by 0. So that's fine. Okay, what about the range of this? Now, sketching this, that's going to be a bit difficult, but we know what Desmos is now, so let's cheat a little bit and see what it looks like. Okay, so we have sine of x divided by, we had cos of x. Here you can just type out the name and it will auto-complete it there. Plus 1/2. Okay, so it looks a bit like the tan function. That makes a bit of sense. We've got sine over cos, so kind of expected. And then we can see all those problem points gives us vertical asymptotes. Well, we know that from high school. the problem points are vertical asymptotes. The target, that's the vertical, that's all real numbers, that's fine. What about the range? Is there anything along the vertical that is not included? Okay, well, we can zoom out. Maybe it has some ending there. No. Okay, so we can zoom out and we see that going vertically, we go all the way to positive infinity. Looking down, it goes all the way to minus infinity. There's no cuts. There's no breaks to it. So what's the target? Real numbers. What's the range? Real numbers. So we can put that in now. So y, all real numbers, that's what we're dealing with calculus. And the range, I'm going to put this as f capital X. Okay, that's my notation that I like to use. You can use the capital R for range. You can write out range fully if you want. That's fine as well. That's all real numbers as well. Okay, we've got no problems there. Okay, everyone okay with that example? Okay, please put your hand up if you lost. Okay, put your hand up if you're scared to put your hand up. Okay, no, good, good, no one's scared. No, you mustn't be scared of me. Okay, so let's just zoom out, zoom in here. Okay, so with Desmos, if you have a problem with zooming, you can press the little house there, and that should take you back to where you started. Okay, so you can move around, you can pan and zoom and look at your graphs, and then you can click that little house there, they'll take you back. Okay, let's think of something else that's a bit crazy. We're not going to actually do the calculation, we're going to do it by inspection. That's another method. If you can draw the graph, like the hyperbola, you can see where the problem points are and you can just put it down. Okay. Yeah, so if you don't need to do the full calculation and you can still provide me with the right answer, that's fine. I'll accept that. That's totally fine. However, if that's wrong and you haven't done any calculation, I can't give you part marks. Okay, so you need to think about that a bit. Okay, someone give me a polynomial, cubic. Okay, someone said 1, so we have 1, good. Another number, 3, good. Okay, let me fill in the rest. Okay, we got a cubic polynomial at the top, quadratic for the bottom. Someone give me a number. Third of 4 there. Let's say plus x squared. Okay, so here we've got a function like this. Now, whenever you have a function like this where you could possibly divide by 0, again, alarm bells. Are we going to be dividing by 0? Well, if you just blindly go through the calculation, you're going to run into some problems. This is where you need to think a little bit more. 4 plus x squared. If you go ahead and just start calculating, you're going to have 4 plus x squared equals 0, x squared equals minus 4, x equals roots of minus 4. Oh, that's a problem, right? You can't do that. So you need to think a little bit. X squared, that is 0 or bigger. 4 plus something that is 0 or bigger, that's not going to be 0. You've got that 4 there, it stops you. So here, we're not dividing by 0. We can't divide by 0. So that's not a problem point. So what is the domain going to be? Real numbers. We've got no problem points here. So it's fine. If this was a minus, let's put a minus there. Now we do have a problem. And we can see that in the graph here. Let's just zoom in a bit there. 4 minus x squared. That can be 0. So please think about it before you start calculating. Don't just take denominator equals 0 and try and solve. Think a little bit and think. 4 minus x squared. Can that be 0? Yes. Why? Well, 4 minus x squared equals 0. can take the x squared over, x squared equals 4, x can be plus or minus 2. Quick calculation, just do it in your head and see, do I need to do the extra work or not? Now we've already got the answer, plus or minus 2. Those are problem points. Let's see what happens with those problem points. X equals 2. 2. There we go, we've got an asymptote there. Problem points in the domain gives us an asymptote in the graph. And the other one was minus 2. Again, problem point for the domain, it gives us that asymptote there. Okay, so please take these two examples as a little bit of warning. Whenever you see something divided by something, don't immediately jump to, can this, set it to 0, see what happens. Just take some time to think, can it actually be 0? Maybe it can be 0, like in this case. Maybe it can't be 0, like in that other case. Okay, so just because you're dividing by something, don't get all trigger happy and think, okay, set to 0, try solve for x. Okay, and then regarding the range, okay, so you can find it by calculation. That's a bit much to do for now, but if you do, you'll see that it can be all real numbers. We don't have any horizontal asymptotes. We'll cover that later. We need to do something called polynomial division. We'll cover that later. Okay. Has anyone done polynomial division? No. Okay, so something new to learn. Okay, so that should be it for today.